Last episode, we found extrema of functions of two variables. We asked where f of x, y is biggest or smallest. Today we change the question entirely. We ask how much of f there is over a region. In one variable, this question had a beautiful answer. The Riemann integral, the limit of sums, the sum of f of x sub I times delta x sub I, which geometrically is the area under the curve y equals f of x. In two variables, the answer is structurally identical. Chop the region capital R into tiny pieces of area delta capital A, evaluate f at a sample point in each piece, sum f times delta capital A, take the limit as the pieces shrink. That limit is the double integral, written the double integral over capital R of f of x y d capital A. Geometrically, it is the signed volume under the surface z equals f of x, y above the region capital R. We will see how to actually compute one, using Fubini's theorem, which turns the double integral into two ordinary single-variable integrals nested inside each other, how to handle general regions described by vertical or horizontal strips, why switching the order of integration is sometimes the whole game, and how polar coordinates make the Gaussian integral fall out in a single line. Let's set the stage carefully. In one variable, the Riemann integral was built by chopping the interval from a to b into n subintervals of width delta x sub I, picking a sample point x sub I star in each, summing the products f of x sub I star times delta x sub I, and taking the limit as the widths shrink to 0. The sum approximates area under the curve, and the limit is the area. In two variables, the recipe is identical, but the ingredients live one dimension up. Replace the interval with the region capital R in the plane. Partition capital R into n small pieces, each with area delta capital A sub I. Think of them as little rectangles, although in general they can be irregular shapes. Pick a sample point x sub I star, y sub I star inside each piece. Form the Riemann sum, the sum of f times delta capital A, and let the mesh size, the diameter of the largest piece, tend to 0. If that limit exists and doesn't depend on which partition or sample points you chose, we call it the double integral over capital R of f of x y d capital A. The standard theorem, due in spirit to Riemann and tightened by Lebesgue, continuous f on a closed bounded region is always integrable. Here is the picture. The blue closed curve bounds the region capital R. The thin pale grid shows one possible partition. I've drawn a Cartesian grid because it's the easiest to visualize, although in principle any partition into small pieces works. The orange highlighted square is one representative piece delta capital A sub I, and the red dot inside it is a sample point x sub I star, y sub I star. The contribution of this piece to the Riemann sum is f of x sub I star, y sub I star times delta capital A sub I, e sub I, the value of f at the sample point, multiplied by the area of the piece. Geometrically, if you imagine z equals f of x, y as a surface floating above the plane, this contribution is the volume of a thin column with base delta capital A sub I and height f of x sub I star, y sub I star. Sum over all the pieces and you approximate the volume under the surface. Shrink the pieces, take the limit, the approximation becomes exact, and that limit is the double integral. Boundary cells aren't quite rectangles, but for any piecewise smooth boundary they contribute negligibly as the mesh shrinks. Now the geometry. When f is non-negative on capital R, the double integral has a clean interpretation. It is the volume of the three-dimensional solid that sits above the region capital R in the xy plane and below the surface z equals f of xy. Each term f of x sub I star, y sub I star times delta capital, A sub I in the Riemann sum is the volume of a thin rectangular column. The sum approximates the total volume, the limit is exact. When f takes both positive and negative values, the integral is signed volume, regions where f is less than 0 subtract. A special case worth flagging, when f is identically equal to 1, every term in the Riemann sum is just delta capital A sub I, so the sum is the total area of the partition, and the limit is the area of capital R, so the double integral over capital R of 1 d capital A equals the area of capital R. This is occasionally useful as a sanity check, and is sometimes used as a definition of area for irregular regions. The double integral is linear. You can pull constants out and split sums. It's additive over regions if you split capital R into two pieces, sharing only a boundary. The integral over capital R equals the sum of the integrals over the pieces. And it's monotone, bigger integrand, bigger integral. These are the same properties the single variable Riemann integral has, just with one extra dimension along for the ride. How do we actually compute these things? We almost never go back to the Riemann sum definition. Instead, we use Fubini's theorem, which was proved in 1907 by the Italian mathematician Guido Fubini and is the workhorse of double integration. The statement, for a rectangle capital R equal to the interval from a to b, cross the interval from c to d, and continuous f, the double integral equals the iterated integral, where you integrate one variable at a time. Concretely, the double integral over capital R of f d capital A equals the integral from a to b of the integral from c to d of f of x, y, dy, dx. You can also do it in the other order, the integral from c to d of the integral from a to b of f of xy dx, dy, and Fubini guarantees the same answer. How does the inner integral work? In the integral from c to d of f of x, y, dy, you hold x fixed, treat it as a constant, and integrate f as a function of y alone from c to d. The result depends on the value of x you held fixed. Call it capital A of x. Then, the outer integral is just the integral from a to b of capital A of x, dx, an ordinary single variable integral. Geometrically, this is Cavalieri's principle. Capital A of x is the cross-sectional area of the solid at the slice x equals constant, and integrating cross-sectional area against x gives volume. Two single variable integrals and you've nailed the double. Let's grind through an example to nail down the mechanics. Integrate f of x, y equals xy over the rectangle capital R equal to the interval from 0 to 1 cross the interval from 0 to 2. I'll do it both orders to demonstrate Fubini. Order 1, the integral from 0 to 1 of the integral from 0 to 2 of xy dy dx. The inner integral is over y from 0 to 2, with x held fixed. So x comes out as a constant, x times the integral from 0 to 2 of y dy, which is x times y squared over 2 evaluated from 0 to 2, which is x times 2, which is 2x. Now the outer integral, the integral from 0 to 1 of 2x dx, which is x squared evaluated from 0 to 1, which equals 1. Now order 2 as a sanity check, the integral from 0 to 2 of the integral from 0 to 1 of xy dx dy, inner integral over x from 0 to 1, with y held fixed, y times x squared over 2 evaluated from 0 to 1, which is y over 2. Outer, the integral from 0 to 2 of y over 2 dy, which is y squared over 4 evaluated from 0 to 2, which equals 4 over 4, which is 1. Same answer either way, as Fubini promised. Geometrically, the volume under z equals xy above the rectangle from 0 to 1 cross 0 to 2 is exactly 1. Note the integrand factors as xy equals x times y, so the double integral splits into the integral from 0 to 1 of x dx times the integral from 0 to 2 of y dy, which is 1/2 times 2, which is 1. Useful shortcut whenever the integrand separates over a rectangle. Most regions of interest aren't rectangles. They're triangles, disks, regions between curves, exotic shapes. To integrate over these, we describe the region in one of two standard forms. Type 1, also called vertical strips, for each x in some interval from a to b, the variable y ranges between a lower boundary curve, g sub 1 of x, and an upper boundary curve, g sub 2 of x. If you slice the region with a vertical line at coordinate x, you get a single vertical line segment from g sub 1 of x to g sub 2 of x. That's the strip. The iterated integral over a type 1 region integrates y first, with limits that depend on x, then integrates x between constants a and b. Type 2, also called horizontal strips, swaps the roles. For each y in the interval from c to d, x ranges between h sub 1 of y and h sub 2 of y. You integrate x first with limits depending on y, then y between constants. The crucial mnemonic, the inner integral's bounds, may be functions of the outer variable, but the outer integral's bounds must be constants. Otherwise, the final answer would depend on some leftover variable. Many regions can be described both as type 1 and type 2. You pick whichever form gives easier limits or a simpler integrand. Choosing wisely turns ugly integrals into clean ones. Here is the picture for a type 1 region. The shaded blue region sits between two curves. The lower boundary y equals g sub 1 of x in blue, and the upper boundary y equals g sub 2 of x in gold, both running from x equals a on the left to x equals b on the right. The red vertical segment is one representative strip. For a fixed x value, y runs from g sub 1 of x up to g sub 2 of x. The iterated integral over this region is the integral from a to b of the integral from g sub 1 of x to g sub 2 of x of f of x y dy dx. The inner integral integrates along the vertical strip. The outer integral sweeps that strip across the interval from a to b. Notice that the inner bounds g sub 1 of x and g sub 2 of x are functions of x, while the outer bounds a and b are constants. That's the type 1 template. Type 2 is the same idea with the roles of x and y swapped, horizontal strips, x between functions of y between constants. Second worked example, this one over a triangle. Let capital T be the triangle with vertices at the origin, at 1, 0, and at 0, 1, the region in the first quadrant bounded by the line x plus y equals 1. Integrate f of x, y equals x plus y over capital T. First, describe capital T as a type 1 region. For each x in the interval from 0 to 1, the strip runs from y equals 0, the x-axis, up to y equals 1 minus x, the diagonal line. So the iterated integral is the integral from 0 to 1 of the integral from 0 to 1 minus x of the quantity x plus y dy dx. Inner integral, treat x as constant and integrate x plus y with respect to y. The antiderivative is xy plus y squared over 2. Evaluate at y equals 1 minus x times the quantity 1 minus x plus the quantity 1 minus x squared over 2. Evaluate at y equals 0. So the inner integral equals x times the quantity 1 minus x plus the quantity 1 minus x squared over 2. Let me factor a 1 minus x out. The quantity 1 minus x times the bracket x plus the quantity 1 minus x over 2, which equals the quantity 1 minus x times the quantity 2x plus 1 minus x over 2, which equals the quantity 1 minus x times the quantity x plus 1 over 2, which equals 1 minus x squared over 2. Nice and compact. Now the outer integral, the integral from 0 to 1 of 1 minus x squared over 2 dx, which is 1/2 times the bracket x minus x cubed over 3 from 0 to 1, which is 1/2 times 2/3, which is 1/3. Geometrically, the volume of the prism with base capital T and roof Z equals x plus y is 1/3. By the symmetry of the integrand and triangle under swap of x and y, the type 2 setup gives the same answer, a useful sanity check. Here's a tactical lesson that pays for itself many times over, changing the order of integration. The same region can often be described both as type 1 and as type 2, and the corresponding iterated integrals look different. One of them might be easy, the other might be impossible. Here is a textbook example. Consider the integral from 0 to 1 of the integral from x to 1 of sine of y squared dy dx. The inner integral asks for an antiderivative of sine of y squared, which is the famous Fresnel integral and does not exist in elementary form. Game over, if you stick with this order. But look at the region. X runs from 0 to 1, and for each x, y runs from x to 1. That's the triangle above the line. Y equals x in the unit square. Rewrite the region as type 2, y runs from 0 to 1, and for each y, x runs from 0 to y. The iterated integral becomes the integral from 0 to 1 of the integral from 0 to y of sine of y squared dx dy. Now the inner integral is over x, but sine of y squared doesn't depend on x. It comes right out of the inner integral. The inner integral is just y. We get the integral from 0 to 1 of y times sine of y squared dy. Substitute u equals y squared, du equals 2y dy, the integral becomes the integral from 0 to 1 of 1/2 sine u du, which is the quantity 1 minus cosine 1 over 2. Done. By swapping the order, an impossible integral became a 30-second exercise. This is a standard move. Whenever an iterated integral has a nasty inner antiderivative, try the other order before giving up. For some regions and integrands, Cartesian coordinates are the wrong tool. If the region is a disk or an annulus, or if the integrand involves x squared plus y squared in a way that cries out for the substitution r squared equals x squared plus y squared, switch to polar coordinates. Recall, x equals r cosine theta, y equals r sine theta. The crucial fact is how the area element transforms. In Cartesian, d capital A equals dx dy. In polar, d capital A equals r dr d theta, and that extra factor of r is everything. Why is it there? Picture a small polar rectangle bounded by r and r plus dr on the inside and outside, and by theta and theta plus d theta on two rays from the origin. Its radial width is dr. Its arc length along a circle of radius r is r d theta. So its area is approximately dr times r d theta, which is r dr d theta. Larger r means longer arc means more area per dr, d theta. That factor of r is the Jacobian determinant of the polar transformation, but you don't need that machinery to see it, the geometry is enough. The general formula is straight substitution. Describe the region in polar as alpha less than or equal to theta less than or equal to beta and r sub 1 of theta less than or equal to r less than or equal to r sub 2 of theta, replace x and y in the integrand by r cosine theta and r sine theta, and tack on the r from d capital A. Here is the polar grid. The blue concentric circles are level sets of rgi, curves of constant radius from the origin. The blue rays are level sets of theta, curves of constant angle. Together they cut the plane into curved cells. The orange highlighted cell is a typical polar rectangle, bounded by two circles at radii r and r plus dr, and two rays at angles theta and theta plus d theta. Its radial width is dr, shown by the red arrow pointing outward across the cell. Its arc length along the inner circle is r d theta, shown by the red arrow along the boundary arc. So the cell's area is approximately dr times r d theta, which is r dr d theta. Notice this scales with r. A polar cell near the origin is tiny, a polar cell far from the origin is fat. The factor of r in d capital A is just keeping honest track of how much area a given dr d theta rectangle actually represents in the plane. Cell sizes are not uniform in polar coordinates. The r is the correction that makes the substitution work. Now the classic. The Gaussian integral, the integral from -infinity to infinity of e to the negative x squared dx, has no elementary antiderivative. You cannot evaluate it by the fundamental theorem of calculus. Yet it has a clean value, the square root of pi, and the polar coordinates trick reveals why. Consider the double integral capital I equal to the double integral over the whole plane of e to the negative x squared minus y squared d capital A. Convert to polar. The integrand e to the negative x squared minus y squared becomes e to the negative r squared, the area element becomes r dr d theta, and the entire plane is theta in the interval from 0 to 2 pi, r in the interval from 0 to infinity. So capital I equals the integral from 0 to 2 pi of the integral from 0 to infinity of e to the negative r squared times r dr d theta. The inner integral is doable. Substitute u equals r squared du equals 2r dr. And notice that the r from d capital A is exactly what we need for this substitution to work, which is the whole point. The inner integral becomes the integral from 0 to infinity of e to the negative u du over 2, which is 1/2. The outer integral is the integral from 0 to 2 pi of 1/2 d theta, which is pi. So capital I equals pi. Now the magic step. Back in Cartesian, by Fubini, capital I equals the integral from -infinity to infinity of the integral from -infinity to infinity of e to the negative x squared times e to the negative y squared dy dx. The integrand factors, so the double integral factors into a product, capital I equals the integral from -infinity to infinity of e to the negative x squared dx times the integral from -infinity to infinity of e to the negative y squared dy, which is the integral from -infinity to infinity of e to the negative x squared dx all squared. We've shown this square equals pi. So the integral from -infinity to infinity of e to the negative x squared dx equals the square root of pi. One of the most beautiful tricks in mathematics, an integral with no antiderivative in one dimension yields to a two-dimensional argument plus polar coordinates. A short history note. The idea of computing areas and volumes by iterated integration goes back to Euler and Lagrange in the 18th century, who treated double integrals informally as sums of slices, a direct heir of Cavalieri's principle. Rigor came in the 19th century with Cauchy and especially Bernhard Riemann, who in 1854 formalized the integral as a limit of partition sums, the Riemann sums we've been discussing. Generalizing to two variables is conceptually direct, but proving carefully that the iterated integral and the double integral always agree took some work. The definitive theorem is due to Guido Fubini, an Italian mathematician who published it in 1907. The Lebesgue version of Fubini's theorem, slightly later, handles much wilder integrands than the continuous case. It's the version probabilists and analysts use today. As per the Gaussian trick we just saw, the polar evaluation of the integral of e to the negative x squared dx is sometimes attributed to Poisson in his probability and heat conduction work in the early 1800s. 3 centuries of refinement compressed into one slide. Let's compress the method into a working checklist. Step 1. Sketch the region. You cannot integrate well over a region you can't draw. Step 2. Choose coordinates. Cartesian for rectangles and polygons, polar for disks, annuli, sectors, and any integrand featuring x squared plus y squared. Step 3. Describe the region in your chosen coordinates. As a type 1, vertical strips, type 2, horizontal strips, or polar region. Step 4. Write the iterated integral with the right area element, dx dy in Cartesian, r dr d theta in polar. Don't forget the r in polar, it's the single most common mistake at this stage. Step 5. Evaluate the inner integral with the outer variable held constant, then the outer integral. Step 6. If you're stuck because the inner antiderivative is impossible, try the other order, or switch coordinate systems. The Fresnel type example we did showed how switching order can convert impossible to trivial. A few sanity checks, integrating the constant 1 over capital R gives the area of capital R, so that's a quick check on your bounds. Symmetry, both of the region and of the integrand, can often cut the work in half or kill the integral outright. Odd integrand over symmetric region equals 0. With these 6 steps and a bit of practice, most double integrals you'll meet will fall in a couple of lines. Recap. The double integral is the two-dimensional analog of the Riemann integral. Partition the region, sum f times area, take the limit. Geometrically, when f is non-negative, the result is the volume under the surface z equals f of xy above capital R. When f is identically 1, the result is the area of capital R itself. Fubini's theorem from 1907 lets us compute it as an iterated integral, one variable at a time, in either order for a rectangle. Over more general regions, we describe the region as type 1, vertical strips with y bounds depending on x, or type 2, horizontal strips with x bounds depending on y, and integrate accordingly. Changing the order of integration sometimes turns a hopeless integral into a clean one, the sine of y squared example. Polar coordinates with the area element d capital A equals r, dr, d theta are indispensable for circular regions and integrands involving x squared plus y squared. We worked 3 examples. Xy over a rectangle gives 1, x plus y over a triangle gives 1/3, and the classical Gaussian, the double integral over the whole plane of e to the negative x squared minus y squared d capital A equals pi, which yields the celebrated integral from negative infinity to infinity of e to the negative x squared, dx, equals the square root of pi. Next episode, we step up 1 dimension, triple integrals, and the 2 coordinate systems, cylindrical and spherical, tailored to problems with axial or radial symmetry. That's double integrals. A 2-dimensional Riemann sum, evaluated in practice as an iterated single-variable integral, geometric meaning assigned volume, and a Swiss Army knife, changing order or switching to polar for when the obvious approach fails. If this helped, like, subscribe, and try today's challenge. Evaluate the integral from 0 to 1 of the integral from y to 1 of e to the x squared dx dy. The inner integral has no elementary antiderivative in this order. Switch it. The region is the triangle, 0 less than or equal to, y less than or equal to, x less than or equal to 1, becoming 0 less than or equal to, x less than or equal to, 1, 0 less than or equal to, y less than or equal to x. Inner, the integral from 0 to x of dy equals x, and the integral from 0 to 1 of x times e to the x squared dx by u equals x squared gives the quantity e minus 1 over 2. Next episode, we lift everything up 1 dimension, triple integrals over 3-dimensional regions, the triple integral over capital E of f of x, y, z, d capital V. Same idea, partition, sample, sum, limit. But now the regions are solids, and we get 2 beautiful new coordinate systems specifically designed for problems with axial symmetry, cylindrical or radial symmetry, spherical. See you there. Given a continuous function, f of xy on a region R subset R squared, the double integral is the limit I int e et rf of xy dA equals ln p to 0, the sum I equals 1 to the nf of xi star yi star delta ai. Where p is a partition of R into tiny pieces of area delta ai and xi star, yi star is any sample point inside the ith piece. Geometrically, when f is greater than or equal to 0, this is the signed volume under the surface z equals f of xy above R. We evaluate it via Fubini's theorem as an iterated integral, choosing vertical strips, type I, or horizontal strips, type 2, to describe the region. For radially symmetric integrands, the polar substitution dA equals r ddr d theta often collapses a hard problem into a clean one, the cleanest example being e int r squared e minus x squared minus y squared dA equals pi, which forces nt minus in f die 2 the in f die e minus x squared dx equals the square root of pi, an integral with no elementary antiderivative. Next episode, we step 1 dimension up, triple integrals over 3-dimensional regions, and the 2 coordinate systems, cylindrical and spherical, built for problems with axial or radial symmetry. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching, see you in the next one.